Okay, lecture 4, half-life of a reaction. Sorry, I drew the first order rate law here because when I printed it out, this came out first rather than lecture 3, so I started writing on the wrong one, so I'm not printing this out again. Here's the, you should know the definition of half-life. Won't go into that, we're just going to do a problem here. A first order reaction has a rate constant of 0.115 inverted seconds. What is the half-life? Well, as soon as you see half-life written there, you know that you need to deal with the half-life equation for the first order reaction, which is given here. If you know K, plug that in, that'll give you the half-life. If you know the half-life, you can solve for K. Not too much we can do here. This is actually just a form of the first order rate law, the integrated rate law that we've put a restriction on, that we deal with the half-life, but that's derived in the book as well. Using the equation is what I'm going to be after. And in the lecture, on-ground lecture, where I will derive this for you, but it's also derived in the book. So let's just use it. We know the rate constant, so we have 0.693. We see that we have 1 over seconds, so we have seconds when we're done. So that makes sense. And we end up with 6.03 seconds as our half-life. So after 6.03 seconds, half of our sample is gone. After another 6.03 seconds, another half is gone, or we're down to 25%. So that's our half-life. Not much more that we can do here. I said in seconds here. If I said I wanted it in minutes, we'd have to convert this. So always check and see what the half-life is. If this came out to be, say, in the thousands of seconds, I'd probably ask you to convert to hours, just to make it more something that you can see. When you put down 18,000 seconds, that's not as easy to tell what's going on as putting it in terms of hours. So just be careful. The half-life of a first-order reaction is 35 days. What is the rate constant of this reaction in inverted seconds? So it's this equation again. It's first order, so it's this equation. And so we know that we want K in terms of inverted seconds. Well, if you put 35 days in here, you'll end up with inverted days. And then you can convert to inverted seconds. I find that a little confusing to do on the fly. I just never do that because what I normally do is convert 35 days to seconds. I don't make it seem like I can't do it, but it's just I just don't normally do it that way. I mean, it's just converting units, so it's not like the end of the world. But again, I'm more comfortable converting to seconds. You have to convert either before or after. I always convert before, and I make less mistakes that way. But if you doubt me, you can always come in and ask. Say, show me if you can convert inverted days to inverted seconds. I said, well, I'll give it a try. Okay, so we have our half-life here, but it's whatever you're comfortable with. You may have learned it that way to convert afterwards, and that's certainly fine. And then we have K. I'm going to just manipulate this really quickly. And we see that we're going to end up with 1 over seconds, which is the unit. Those are the units we should have. I'm going to do the calculation very quickly. And we end up, I'm going to put it down here. Oops. We have 2.29 times 10 to the 367 inverted seconds. So we said the half-life is 35 days. That's a long time for a reaction to go. So we should expect K to be very small, and it is. So 35 days is 840 hours, which is about 3 million seconds, 3.02 times 10 to the, and then 6 seconds, and then times, just recalculating it, so, yeah. And that's the deal. All right, let's do another one here. Now it's a second order reaction, has a rate constant of 0.0816 seconds. That can't be right, it's second order, so the rate constant has to be inverted seconds, inverted concentration, because concentration is part of the second order reaction. What I did was I think I just copied it from the previous problem. The half-life for a second order reaction involves the concentration. Now the reason it does is because the second order reaction involves two molecules. So as the molecules are used up in the reaction, they have a harder time finding each other. So as the time goes on, the half-life becomes longer because it takes more time for the molecules to find each other. So it is concentration dependent. The first order reactions are not. So we needed to have that in there. And if you put in the units, even if I didn't notice it here, I would have noticed it as we went because we wouldn't be able to cancel the units as we need to. Now they want what is the half-life in seconds, and we put in what we know here. It's 1 over, now K is 0.0816 inverted seconds, inverted molars. Now I had it inverted molars, inverted seconds, same thing. I'm just putting it in this form because I know that we have to cancel the molars. So molars cancel. We're left with 1 over inverted seconds, so that's seconds. And we get 10.2 seconds. So second order reactions involve concentration. So you need to have the concentration somewhere. If it's not listed, then it's not a second order problem. I do have it listed. The big thing is I made a mistake on the units, but if I had forgotten to put the molars in here and you got to this point, it was just inverted seconds, you'd end up with, what would you end up with? Seconds per molar. Well, that's not a unit of time, so we know that there's a mistake there. So if that happened on the exam, you'd want to come up immediately. It doesn't often happen. I quadruple check everything, but but the units again saved me from having to get all the way through this video and realizing I made some mistake. So half-life for a second order reaction is 35 days. What is the rate constant of this reaction I got the units right there, if the initial concentration was 0.1 molar. Okay, so the half-life, let's write it out here, 1 over K times the initial concentration. So the half-life, now we want, I'm just going to leave it as is, but you have to solve for, you can certainly solve for K first, and then K would go over here, the half-life would go here. I'm just going to leave it in this form. But 35 days, what was that? We need it in seconds, so it was 3.02 times 10 to the 6th seconds for our half-life. 1 over, what is the rate constant? We don't know what K is, and our concentration was 0.1 molar. All right, so if we, let's see, so we bring K over here. So K will then be equal to 1 over 3.02 times 10 to the 6th seconds times 0.1 molar. And we have inverted seconds, inverted molars. That looks like the right units. And K is going to be 3.31 times 10 to the minus 6 inverted molars, inverted seconds. And I'm going to just redo this real quick. So 3.02 times the concentration there. And yep, that's the guy. All right, let's try another one here. See, these half-life problems are pretty quick because they're very short equations. There's only a couple of things that we have to deal with. Zeroth order. So this is the half-life for zeroth order. It's the concentration over 2K. So we need to know that equation. A zero order reaction has a rate constant that is 0.00333 molars per second. Same units as for the integrated rate law, and that's because this is taken as a version of the integrated rate law, so same units. What is the half-life in days if the initial concentration is 1.20 molar? So let's put everything in here. We have 1.20 molar. 2, K is 0.00333 molars per second. We can see that molars are going to cancel, then it's 1 over seconds, so seconds when we're done. And the big thing is, if you don't see how I did something, as far as the math, I'm not doing anything mysterious here. This is a level you should be at. So if you're looking and say, I don't get this, I don't understand how he just did that, come and see me as soon as possible, or your instructor as soon as possible, because this is something that should be a very quick thing. As I do this out, you should be doing it in your head. So it's not something that it should be considered advanced at this point. It's something that you should know. And if you don't, that's okay. You just have some work to do, and let me know. So we have half-life in days. Our half-life is in seconds, 180 seconds, and we got to convert that to days. So divide by 3,600 seconds per hour. That gives us hours. Divide by 24. That gives us days. So it's going to be 0.00209 days. You can just write D. When you know what you're dealing with, you can just leave it. You don't have to put days. You can just put D. So 1/8. That will give us hours. And then, yep. And that's the deal. 6. The half-life for a zero-order reaction is 22 hours. What is the rate constant of this reaction? If the initial concentration is 0.1, I don't know. Oh, this looks really familiar. Okay, well, the first thing is our rate constant has to be in molars per second. Looks like I just took that other problem. Sorry about that. That was second order. One and half-life, so let's just write it in here. Just trying to give you some variations. So they gave us, this time they gave us the time in 22 hours. We need the rate constant be in molars per second. So we need to have the 22 hours changed to seconds. So 22 hours, each hour is 3,600 seconds. So this should be 7.92 times 10 to the 4th seconds. The initial concentration is given here, 2K. And then we solve for K, so it's going to be 0.1. Now let me just rearrange. What we'll end up with is 0.1 molar over 2 times 7.92 times 10 to the 4th seconds. We see we end up with molars per second. That's what we want. So 0.1 divided by 2 divided by 7.92 to the 4th. And this comes up to be 6.31 times 10 to the minus 7 molars per second. We should expect K to be very small because the half-life is an extremely long half-life. If you had reactions in the lab that were 22 hours for a half-life, we never accomplish anything. Most of our half-lives for our reactions are on the order of seconds. And that's the deal.